Welcome back. And the next section is the new statistics in action, the complicated stuff. So thank you for joining me for it. The new statistics how? And this 8-step plan, I think, maybe is one of the big takeaway messages. And an 8-step plan for doing good new statistics research, good research integrity research, I don't pretend for a moment it covers all bases, but it has some important elements. The first is, possibly the most important, use estimation thinking. So state your estimation questions, your research questions, as how much, to what extent, how many. So it's not, I wonder if there's an effect, but I wonder how big the effect is. The answer might be 0, but think in terms of estimation. And I've been trying to do this myself for some years now, and it really requires discipline. It's so easy to say, I wonder if that'll make a difference. I wonder if this is bigger than that, instead of saying, I wonder to what extent, I wonder how big, I wonder how large. And so I invite you to train yourself. How much, whenever you see a whether or an if, how much? And this almost guides us into doing estimation because the answer will have to be this much, plus or minus so and so. So identify the effect sizes that correspond to the questions, which might be, say, effect size might be a difference between some means. Declare full details, pre-declare your study if you can, maybe using OSF. Do the experiment. Calculate point and interval estimates, and if you can, make a picture, including confidence intervals. Interpret, admittedly and deliberately using your skilled judgment in context. Use meta-analytic thinking at every stage, so we're building a cumulative discipline, and make a full report publicly available somehow. Okay, it's nice if it's in a good journal, but at least it's got to be out there so future meta-analysts can draw on it. Now, you might look through this list and say, well, yeah, pretty obvious, but now go through it again and note how every step pretty much is different from current practice. So this might make reasonable sense, particularly in an estimation world, but if we really did adopt this fully, we would be changing practice quite a lot and changing our teaching and changing our expectations quite a lot. And so, of course, we need to weigh up carefully the pros and cons, but I argue it is worth doing. So that's a takeaway message. The new statistics actually doing it, I talked about that a little bit before, so I'll just say briefly, actually doing it, I recognise immense practical problems, although day by day things are getting easier as more journals come on board, as the publication manual recommends, as more resources are available. And one of the important aims in the tutorial paper in psychological science was to give a lot of references and links to online calculators and so on. So if you are interested in structural equation modelling or multivariate or whatever, there's a chance that I can suggest a couple of sources. And many of them are quite recent, so this is rapidly developing, and just quite recently we're getting more and more possibilities of doing estimation in many situations. And what you should do, of course, is to explain and justify your data analytic approach, maybe with some references to back it up. Would I ever add p-values? Well, I confess in the past I have if I really felt a lot of pressure, but maybe in a footnote and then don't refer to them. Do everything else in estimation, although these days you might just more often get away doing it properly without mentioning p-values. Okay, let's consider a sort of more grown-up, more complicated, more realistic sort of situation, say an RCT, where I've got 2 groups, a control and a treatment group, tested it 4 times from pre-post, follow-up and follow-up. So I've got means at each of these 8 points with 95% confidence intervals. Can we interpret these confidence intervals? Can we use these confidence intervals to answer our research questions? And the answer is, well, for between groups, yes. For repeated measure, no. needs a little bit of unpacking. It was all explained actually in this paper with Sue Finch in 2005 in The American Psychologist, which is now available for a free download from this link, courtesy of the APA. And my general approach to this sort of design and more complex designs is to recommend planned contrasts. And Rosenthal, for example, has argued strongly for many years that, okay, doing a knee-jerk 4x2, look at the interactions, do post hoc tests approach to this sort of thing, which may have been traditional, is far from ideal in many cases because you in fact have specific research questions. You might be particularly interested in the difference of the differences, the difference in the gain score for control and treatment. Okay, that's a 1 degree of freedom interaction, estimate it, put a confidence interval on it. You may be interested in what happens between post and follow-up 2 or some other contrast or comparison, plan a small number of those, estimate, put a confidence interval on, and then you're in home territory. Use any of the 5 ways to interpret. Let me say just a little bit about this between versus repeated. You know that think t-test, 2 independent groups, and you can simulate and play around in ESCI with that. Or paired design, you can simulate and play around with that in ESCI. They're different. So independent groups, you know that here we typically assume homogeneity of variance, use this pooled standard deviation under here to calculate our t-value, or in fact to calculate the confidence interval on the differences. And these are based on the estimated standard deviations in the 2 separate groups. The paired or matched design, in striking contrast, very different, uses the standard deviation of the differences. And this is a sensitive design because this standard deviation of the differences often is quite small because of the correlation between pre and post. And that's good news. It's a sensitive design. So, looking at it in pictures, here we have 2 independent groups, A and B. We have a floating difference axis, so I've got 0 lined up with one of the group means, and I can measure and examine the difference on this axis here. It's about 30 points, and I can plot that delta triangle for a difference, and I can put a confidence interval on that difference. Now, when we've got independent groups, this confidence interval is calculated using that pooled standard deviation. So it's calculated based on the standard deviation of this group and the standard deviation of that group. In other words, it's calculated using the same information that I use to calculate these 2 separate confidence intervals. So this confidence interval is determined pretty much by these other 2. And if I know these other 2, I know that this one typically is about 1.4 times as long, root 2 with a bit of adjustment, as long as either of these. So if you just give me these, and I want the confidence interval on the difference, I can actually eyeball it. Because I can eyeball the difference here, I can imagine a confidence interval 1.4 times this long on that, and so in my mind's eye, I do this. It also means that it's relevant to note whether these 2 overlap when we've got independent groups. Because the length of this interval is related to the length of these, and I interpret this confidence interval against this floating difference axis. Equivalently, I look and see whether these overlap. Now, contrast that strongly with the paired case. Here I've got, say, pre-test and post-test, and here I've got the difference axis, and here I've got the mean of the differences, and we've got a short confidence. Are we happy? We are very happy. A short confidence interval is good. Why is it short? Because we've probably got a pretty high correlation between pre-tests and post-tests. And in practice, it's not uncommon to have correlations of 0.7, 0.8, or even more between repeated measure values, and that's terrific. That means that we've got a sensitive experiment. We're estimating this difference, this change quite precisely, relatively precisely. Each participant is their own control, and so when we can use a repeated measure study, there are disadvantages, of course, but when we can use that design, that's terrific. But the fact that this confidence interval length reflects strongly that correlation means that if you just give me these two confidence intervals, there's no way I can assess this change. Because there's no way that I can eyeball or figure out, without knowing that correlation, the length of this confidence interval. So I can't have any overlap rule for these separate confidence intervals because I don't have they don't provide the information needed to get what we really want, which is this confidence interval here on the differences. So it's worth reflecting on the difference between these two and read that 2005 paper on inference by eye if you'd like a more measured and detailed explanation. Now this overlap rule, when we do have independent groups, when two 95% confidence intervals just touch, so in this situation, well then we have a reasonable amount of evidence, moderate amount of evidence that there's a true difference. It corresponds to p round about 0.01 if you want to think in those terms. Varies a bit depending on the relative lengths of these intervals and the relative sample sizes, and we discussed that in this article there. But even when you have a moderate amount of overlap between these two 95% intervals, you've still got some evidence, corresponds to about p 0.05 if you want to think in those terms, when a couple of simple conditions are met. Now if you're thinking that this amount of overlap here, that doesn't really seem compatible with a difference, think of the cat's eyes. And the only bits that do the overlapping are the thin bits. And so if only the thin bits overlap, well maybe it's a bit more reasonable that when we've got this configuration of overlapping independent 95% confidence intervals, we do have at least some evidence of a difference between these means. I discussed that in more detail in this paper in Statistics in Medicine. If you overlap sufficiently, there's no significant difference. How nice. So if we come back to our RCT, we can now look at these various comparisons. So here we've got a repeated measure in the control group, and here we've got an independent group but a repeated measure within that other group, the treatment. So if I wanted to compare post-control with post-treatment, is it okay to look at these confidence intervals? Yes, it is, because these two means are independent. And the fact that they're not overlapping, the fact that there's a big difference compared with the length of these intervals means we've got strong evidence that yes, in fact, there's a difference there. But now what about this difference? We look at this and say, I wonder whether there was a bit of falling back from the post-test to the first follow-up in the treatment group. And I'm interested in that difference. How can I interpret that difference? Well, what I need is the confidence interval on that difference itself. And since this is a repeated measure, these confidence intervals do not give me the relevant information. So even if the fine details there are a bit tricky to grasp at a 10-second presentation, we need to recognise that when we look at a figure with means and confidence intervals, we have to ask some important questions, and one is, what's the design? And which is a repeated measure, which is between? And of course you know that, but this makes it very salient. And it's a great shame that our graphic conventions don't shout this at it. I've put in a line joining these means, and that's quite a good convention when we've got a repeated measure, but it's not uniformly followed, unfortunately, so we can't rely on it. In this paper, this chapter, we discuss estimation approach to analysing these sorts of designs. And so if we wanted to look at this difference, we might have to have a different plot here and look at the, this is the change score from pre to post or post to follow-up or something for the control group and for the treatment group. Here are our reference points for the effect size, and we can interpret these two confidence intervals, which are now on independent groups, so it's relevant to note that they're not overlapping. Cohen's D, a standardised effect size, known in medicine as often as the standardized mean difference. Cohen's d, well, I'd call it a z-score, you might call it a z-score, is a number of standard deviations, as simple as that. But in fact, there are quite a few tricky things with Cohen's d. Cohen's d is the original effect size in original units, milliseconds or whatever, divided by a suitable standard deviation. And this standard deviation is like the measurement unit. Why do we use d? Because we often use different scales to measure the same thing. Anxiety, I'm sure there are any number of instruments that measure anxiety. Medicine is very critical about using these standardized effect sizes, some writers in medicine, because of the problems I'm going to outline. But they have the luxury that if anyone measures blood pressure, I mean, they do it in millimetres of mercury. It's not done differently in different countries or different research traditions. Whereas just about anything in psychology, very likely there'll be a number of different measures for it. So if we're going to integrate results using meta-analysis or even compare results across these measures, we're probably going to have to use a standardized effect size such as Cohen's d. And so we have to grapple with these difficulties. And our sample d calculated from our data is a point estimate of the population delta, as in my dance of the p-values examples. And we've mentioned Cohen's benchmarks of size, small, medium, large, but arbitrary, used as a last resort. Okay, slightly tricky stuff coming up. Let's take an example. I'm working with IQ scores. I've got a control group. You can make up a little cover story with a mean of 110, standard deviation 12. An experimental group, mean of 120, standard deviation 16. I want Cohen's d for the difference between these two independent groups. So it's the effect size divided by some standard deviation. Now, my first question is, which standard deviation makes best sense as the unit of measurement? Well, it's the population standard deviation for whatever IQ measure, IQ instrument I'm using. Next thing is, what's the best estimate we have of that standard deviation? And there are a number of options. In this case, we might actually know the population value because the test was standardized in some relevant population, reference population, that we judge to be relevant for our study. I've been involved in situations where we know a population reference population standard deviation, but we did not judge it relevant. But for IQ you might decide, and therefore use 15, and so D is simply the difference between the means divided by 15, and you get this value. But if for some reason you didn't know that or didn't want to use it, didn't think it relevant, what are you going to use? Well, you've got one estimate of the control standard deviation, one of the experimental. You might regard the control one as sort of like a baseline case, a reference case, and decide to use that. And so you'll use D, this difference, divided by 12, the control standard deviation, you get this value. Or you might say, well, look, homogeneity of variance is perfectly fair in this situation. I think not too bad. So I'm going to get a more stable estimate of standard deviation if I pool. So pool from the 12 and the 16, get something roughly 14, and calculate. And so which is Cohen's d? It depends on the judgments and assumptions you make. And therefore, unless you tell us how you've calculated your d, we can't interpret your number. Whenever you see a Cohen's d, you need to read more thoroughly or use other ways to find how that d was calculated. Otherwise, we can't make any sense of it. Let's look at the third option, which is probably the most common, pooled from the two groups. So d is the difference between the means, and on the bottom we have this pooled estimate of population standard deviation pooled from our two groups. So we've got estimation both in the numerator and the denominator. We've got sampling error in both top and bottom. And the thing on the bottom is really our measurement unit. But the trouble is, if somebody else did the experiment, or if you did the experiment again tomorrow, you would get a different value. And yet that's our measurement unit. We are using the rubber ruler. Now you might not be able to see this, but this is a ruler, and it's got white marks on it at equal intervals, and they represent our estimated standard deviation. And the trouble is, as you repeat your study, you'll get slightly different estimates each time. And so your measurement units will change. And so you're measuring on the rubber ruler. And so if you say it's D of 0.5, I don't know that whether you were using that ruler or this ruler. Think of back in the days when the foot was a unit of measurement. I gather in this country it still is. But it was standardised. It was the king's foot. But let's suppose everybody used their own foot. So my son would be using a ruler like this, and perhaps somebody with nice dainty little feet would be using a ruler like that, and you tell me that this book is half a foot wide. It's very hard to make sense of that unless I know where your ruler was. And that's the sort of problem that leads some medical researchers to say standardised effect sizes are so problematic we shouldn't use them. But we don't have that luxury. We have to grapple with them. Okay, the paired design, what should we do? Here's the example. Let's suppose a healthy breakfast increases the score on an IQ test by 2 points. And let's suppose it does that really very consistently across people. So somebody on 72 goes 74, somebody on 140 goes 142, and so on. And we do a nice little experiment, and some people come in, and on Wednesday they have a usual breakfast, then 2 weeks later they come in and they have the healthy one. And other people come in, have it the other way round, and we do repeated measures. How are we going to calculate D? So let's assume we've got 110 as the mean for the ordinary breakfast, 112 as the mean for the healthy. We've got standard deviations of 12 and 16, which is perfectly plausible. We've also got the standard deviation of differences, now made at 0.5. So that's suggesting that people tend to have a very consistent improvement of around about 2. It's 1 or 1.5 or 2 or 2.5, pretty close to 2. So this is a very small standard deviation of all those personal difference scores. So what should D be? Well, it's effect size divided by standard deviation. Well, the effect size is easy enough. It's just 112 minus 110 is 2. But should we use the population standard deviation and get 0.13? Possibly. Should we use the usual diet, the usual breakfast, as a sort of control baseline? Okay, we get 0.17. Should we use the pooled from the pre-test and post-test, or average? Well, you can argue for that, 0.14. But consider there's another more drastic option here. For the paired t-test, or the confidence interval on the mean of the differences, we actually use the standard deviation of the differences as our critical thing. That's why we got a very short confidence interval on the difference. We'd have a beautifully short confidence interval on the difference in this design because this standard deviation is so small. Should we use that as the unit for D? But in fact, no, it doesn't make sense at all. To say that the difference between regular and healthy breakfast is 2 IQ points divided by the standard deviation of the differences and get a D of 4, that's ginormous. That just doesn't make sense. And in an early paper with Sue Finch, 2001, we debated this. In Cohen's book, he allows for the possibility of using this standard deviation of differences for Cohen's D. And Sue was arguing, look, I'm sure there are examples. And I've been looking for 15 years for somebody to give me a convincing example where it made conceptual sense to use this standard deviation of the differences. And I haven't found one yet. Maybe you can come up with them. So the message here is with Cohen's D, think carefully about what makes conceptual sense as your reference point. And think that you want it to be some standard deviation, some measurement unit that is likely to make sense across a number of different studies or even research fields and across a number of different research designs. Somebody else might do this healthy breakfast study and use independent groups. And this 0.5 for the differences they would have no such quantity to consider. And they would probably use 15 or something like that. Well, the influence of a healthy breakfast surely should be some absolute thing, have some value in the world that doesn't depend on just the fine detail of your experimental design. So I'm mainly pointing out that for Cohen's D, you've got to grapple with the conceptual meaning and make decisions. as to what you calculate and how you do it. Confidence intervals for Cohen's d, a bit tricky, let Esky do it. You need the non-central t distribution, which is terrific, lovely hump, but that's another story. You can read the fairy tale about it at that link. And in this article, Fiona and I evaluate an excellent approximate method of calculating confidence intervals on D. Unfortunately, a couple more tricky things. D is not an unbiased estimate of delta, unfortunately. And to get an estimate of the population value, we need to apply this correction factor. And when we've got very big samples, 50 or more, it hardly makes any difference. But when you've got 10, 20 or 30, well, it makes a few percent. We really need to do it. Now, I call this adjusted, this unbiased value, D unb. D unb. D unbiased, so it's totally unambiguous. And usually this should be the thing of choice because we want unbiased estimators. Unfortunately, next tricky thing, the terminology in this area is a nightmare. Hedges G, named after Larry Hedges, very notable meta-analyst amongst other things. Hedges G, back in the 80s when he introduced it, it had a particular meaning, pooled standard deviation. But these days it's used with a totally different meaning, that is unbiased version of D. How this came about, I have no idea. So the only safe policy, I think, is to do what most people do, just call it Cohen's D, whatever it is, even if it doesn't quite match Cohen's original definition. But make very sure that you explain how you calculated it, pooled or not, control or not, unbiased or not, and then we'll be able to interpret it. So the take-home messages with Cohen's D, it is this ratio. It's really worth having. Choose the standard deviation unit carefully, and then the best estimate of that. Maybe that will involve pooling over a number of different groups, or even a number of different experiments. Do a little meta-analysis of your standard deviation estimates so that your rubber ruler doesn't bounce around so much. That could be a good strategy. We've done that on occasion. Report how it was calculated and beware the rubber ruler. And then interpret in context. And we've discussed a bit about the challenges there. In some situations, 0.1, a D of 0.1 might be worth $1 million, save 1,000 lives. In other situations, a D of 1.0 you perhaps don't care about. I can't quite think what it might be, but you need to judge in the context. I'm looking here briefly at a couple of different effect sizes and confidence intervals on those effect sizes. And just as a for instance of an effect size that's very familiar but has an asymmetric confidence interval, I'm going to take ordinary Pearson correlation R. And let's go over to Esky. And there it is. So here I can specify an R value, and I've got a 95% confidence interval on that R for a particular sample size, 30 in this case. And the R value is 0.6. And what I'm going to do is just show you what happens as I change that R value. Isn't that a bit weird, eh? So here it's long and symmetric, and as we get close to the boundary at 1.0, it gets shorter and it gets more and more asymmetric. Well, it's still a confidence interval. Could I explain why? Well, we use Fisher's R to Z or R to Z transformation, and you can illustrate it here. Here is the curve of that transformation. So if we take our R value of 0.6, we take it out to the curve, reflect it, drop it down onto this Z or Z axis, we get 0.693. That's the Fisher's transform value. We calculate a confidence interval in that space, and there it is symmetric. And there it is, just that long like that. And then we reflect those back using the inverse transformation, and because this curve is curved, we get a shorter upper Moe and a longer lower Moe. And so that's an illustration of how a transformation, which is chosen to sort of stretch out the limits of this limited scale from 1 to -1, results in a confidence interval that's asymmetric. And many other confidence intervals are asymmetric. In fact, the one for Cohen's D is a little asymmetric. And so that's fine. Often we find that confidence intervals are embarrassingly wide, discouragingly wide. And confidence intervals on R is certainly a case in point. This was, I think, for n equals 30, and you could go into ESCI and try for n equals 100, it would be shorter, for 20 it would be longer, and so on. Cohen's benchmarks for R, 0.1, 0.3, 0.5, are particularly inappropriate in lots of cases. This is a great illustration that he was right in saying these are arbitrary. For example, if you're using your correlation to estimate the reliability or validity of a scale, well, you might regard 0.8 as only fair average quality, certainly not very large. There's another page, another ESCI module, ESCI effect sizes, I'm not going to illustrate, but it is the one that's primarily designed to do calculations for you. So if you want to calculate confidence intervals on correlations or the difference between two correlations, boy, they can be scarily wide, then ESCI can help you there. Confidence interval on a proportion is another example of a different effect size measure, proportion, that usefully can have confidence intervals on it. So if we have just a simple 2x2 frequency table, the knee-jerk reaction in the past would be to reach for chi-square and test the null hypothesis that this classificatory variable, drug placebo, is independent of survived, died, and in fact you get a p-value about 0.04 something. But I'd prefer to estimate. And assuming we've got independence here, I can say, well, look, the survival proportion for drug is 17 out of 20. And the survival proportion for placebo is 11 out of 20. What's the difference? And can I put a confidence interval on it? Yes and yes. The difference is 0.3, and ESCI effect sizes allows you to calculate the confidence interval on that difference, which is 0.02 to 0.53. Now, the fact that that does not quite include 0 is perfectly consistent with chi-square giving a p-value of 0.04 something. But I'd argue here, as usual, the estimation result is more informative because it tells us that we've got a pretty poor estimate, a pretty imprecise estimate for the difference in survival rates between these two. Using odds ratios and log odds ratios would be another approach here. But the main point is, even in situations where traditionally we've reached for NHST, there may well be a good estimation alternative. And here's, I think, my last example of a use of confidence intervals. This is a beautiful piece of work by Wayne Belliser. They in Rhode Island, they work on enormous data sets, and they have developed the trans-theoretical model of behaviour change. So a stage model of, for example, people giving up smoking. And they've got a dozen or however many it is, 15 predictors here. And over the years, with enormous data sets for behaviour change in different areas, they've developed a quantitative model of the relative contributions of these predictors. And they've got to the stage of saying, well, we're going to predict that this particular variable or that has a 0, a small, a medium, or a large influence. And we've quantified what we mean by small or medium in the context drawing on partly skilled judgment, partly previous experiments. And we express these in terms of omega squared, proportion of variance attributable to these things. And then they said, right, acid test, let's test this quantitative model on a totally new data set, 4,000 smokers here. And from the smokers, they estimated point estimates and confidence intervals from these 4,000 data points for each of these predictor variables. And so for reinforcement maintenance or whatever it is, we observed in the data an omega squared of about 0.02 or something, and this confidence interval on it, whereas the theory predicted this dot, and so, well, we haven't quite hit it. But I think they've done remarkably well here, and in a couple of cases where the predictions are way off from the data, this clearly points the finger to areas of the model that need investigation or further development. And this seems to me a beautiful example of estimation helping to build a quantitative discipline, making us more scientific, have a more nuanced and quantitative view of the world. So, I've gone quickly through a number of different designs, a number of different things to think about with estimation, a number of different effect size measures with confidence intervals. Pictures to take home. Here is an RCT, 2x4. How do we interpret? Here is an asymmetric confidence interval, and here's the reassurance of the cat's eye, which we can apply to any confidence interval we like. I talked about Cohen's D and the rubber ruler, confidence intervals to assess model fit. And there's more on all these things in the tutorial paper. So let's take one question on this section. I'm sure there are 1,000 you can ask. Lots I could make up, but yeah, in the front row.
So obviously, a smaller confidence interval is better. But how do you address fields and subdisciplines where a larger sample size is really difficult to obtain, particularly for graduate students? So for my own data, I do hormone research. So each participant costs $80+, and I don't have my own funds. So how, is a large confidence interval useless or?
This is a very important question, and especially important for our discipline. Cohen thought, when he introduced his work about power in the 60s and 70s, that if he pointed out to people in psychology that, you do such low power experiments, we'd all go, oh boy, we better improve, hadn't we? Well, whether or not we heard his message, we didn't improve, we still use low power. And correspondingly, as Cohen said, perhaps the reason that psychologists don't use confidence intervals is they're so embarrassingly wide. And that may well be true. I mean, it's discouraging to follow my advice and report your result as 17 plus or minus 14. You go to university to tell me the answer's somewhere between 3 and 31? I could have told you that without getting out of bed. Sort of seems more reassuring to say, I looked at it and it's significant. Well, okay, 0's not in that confidence interval. But it's a serious question. And really, part of the research integrity thing is telling us we just have to find a way to do better, to have more informative experiments. And I've brainstormed endlessly in our department, how can we get graduate students, say, who have to have a project that is very limited in time and resources, do something worthwhile. And so we do things like say, well, look, if we have 4 people work on different aspects of the problem and we can meta-analyse, we're making progress. If we can pick up a promising project from last year that just wasn't enough really to cut it and do it again plus a variation and meta-analyse, and variations on that theme. And I'll talk a bit more about that in the next section. So this is a good lead-in. The next section is planning good studies. And so for this main section about effect sizes and confidence intervals, thank you for your attention.